we will discuss the basics of units and dimensions, as we will be looking at actual examples in this class, and we'll need to be able to talk fluently about physical quantities and their dimensions. All physical quantities have units of some kind, with the possible exception of angles if measured in radians. Thankfully, not something we'll be dealing with. There are 7 basic units, and all other units can be made up of those 7 in some algebraic way. In this class, we will only be using the 4 most common of those basic building block units. They are first length with units of meters, time with units of seconds, mass with units of grams, and temperature with units of kelvins. We also introduce similar units to be able to discuss different orders of magnitude. So, for instance, a centimeter is 0.01 meters. A kilogram is 1,000 grams, and a millisecond is 1/1,000,000th of a second. These conventions can be used for any of the units that we discuss here, and we use basic algebra to convert any quantity into the 4 basic units above of meters, seconds, grams, or kelvins. All other units for any other quantity can be expressed as an algebraic combination of the basic units. So, some examples. First, we have velocity, which can be expressed as meters over seconds. We also have acceleration, which is meters over seconds squared. We also have the quantity of volume, which is meters cubed, or we also say cubic meters. Force is expressed in terms of a unit called a newton, which is kilograms times meters per second squared. And finally, energy, where energy is expressed in a unit of joules, which is kilograms times meters squared over seconds squared. There are 2 ways of combining the 4 basic units. We can either combine them algebraically or using calculus operations. First, we're going to talk about how to algebraically combine units. Algebraically, we can either multiply 2 quantities or divide them. To determine the resulting units, we simply multiply or divide the units of each individual factor. For example, a liter is a unit of volume, and a liter is defined to be the volume of a 10 centimeter by 10 centimeter by 10 centimeter box. We know how to compute the volume of this box. We simply multiply the dimensions of all 3 sides. Therefore, 1 liter is defined to be 1,000 centimeters cubed, since we are multiplying 3 quantities of centimeters by each other. So we get centimeters cubed, or cubic centimeters. From physics, we know that force is equal to mass times acceleration. Since we know the units of both mass and acceleration, we know the units of force can be given by kilograms times meters per second squared. The use of kilograms versus grams or micrograms is purely conventional. It is possible that force can have units of grams times centimeter per microsecond squared. However, the units of newtons has been defined to be kilograms times meters per second squared. A final example has to do with kinetic energy, which is measured in joules. A formula for kinetic energy is 1/2 mass times velocity squared. The units of velocity is length over time, so the units of joules is given by kilograms times meter per second quantity squared, which is kilograms times meter squared per second squared. Notice that the simple algebra is done to the units to determine the more complicated combination of units. The second way of determining complex units is by using calculus operations. The 2 basic calculus operations are differentiation and integration. So we're going to talk about how we can determine the units of a derivative and the units of an integral. When we differentiate a quantity with units, the units of the derivative are the units of the dependent variable over the units of the independent variable. So for instance, the units of dy dx are the units of y over the units of x. As an example, let's assume that s of t is a function which represents the position in units of kilometers, and t is a variable which represents time in units of hours. We know that velocity is the derivative of s with respect to t, so the units of velocity would be kilometers per hour, units of s over units of t. Next, if we consider acceleration, which is the derivative of velocity with respect to time, we see that the units of acceleration will be the units of velocity over the units of time. So it would be meters per second, or combining this and simplifying, it would be meters per hour squared. With integration, the opposite happens. We multiply the units of the dependent variable by the units of the independent variable, as opposed to divide with derivatives. So the units of the integral of y with respect to x would be the units of y times the units of x. So for example, let's consider force as a function of space. Force is in units of newtons, and x, our space variable, will be in units of meters. We know that we can compute work by integrating the force function with respect to x. So the units of work would be in newtons times meters, or we sometimes say Newton meters. We can also look at this and see that this is exactly the units of joules. So this tells us that work is a type of energy. Next, we are going to discuss how to determine the units of a particular variable that we may not know the units of. To do this, we use a concept called dimensional homogeneity. This says that all terms in an equation must have the same units. And this should make intuitive sense, since we really shouldn't be able to add length to time, or be able to subtract force from energy. When we are adding two terms together, really it makes sense that they should both have the same units. They should both represent the same type of thing. And of course, this really only works in equations that represent some aspect of the real world. But any equation that we will discuss in this class will represent an aspect of the real world and therefore will be dimensionally homogeneous. Let's consider an example. First, we introduce some notation, which represents the unit of a particular quantity with square brackets. So for instance, here we have the units of some variable z is represented by square brackets around the z. So let us say we have a quantity x, which represents the position, and the units of that quantity will be centimeters. T represents time with units of seconds, and m is going to represent mass with units of kilograms. And finally, we're going to have a differential equation that relates all of these variables together. This is actually the equation for a spring mass system, with this variable k being the spring constant. Our goal here would be to determine what are the units of the spring constant k. So first, we figure out what are the units of that first term, m times the second derivative of x. We know that the units of a product is the product of the units. So the units of the first term will be the units of m times the units of the second derivative of x. Well, the units of m, that's mass, we know that's kilograms, and the second derivative of x represents acceleration. So it will be the units of centimeter per second squared. So this gives us the units of that first term. For the second term, the units will be the units of k times the units of x, which are centimeters. So the second term units will be the units of k times centimeters. And dimensional homogeneity says that the units of both of these terms have to be the same. So the units of k times centimeters has to be the kilograms times centimeters per second squared. Now the goal is simply to solve for the units of k. We can divide both sides by centimeters and determine that the units of k will be kilograms per second squared. This general technique can be used whenever an equation is given, and almost all of the quantity units are known except for one, and we can solve for the units of that one unknown quantity.